Right, good evening everybody. Welcome to the engineering group's latest evening meeting. Tonight we have Tim Blower of Mott MacDonald, who's going to be presenting on the Banja Hydropower Dam project in Albania. Before I welcome Tim to the stage, we've just got a few health and safety points to go through. There's no drill planned tonight, so if the alarm does go off, you'll have to exit if you're nearer the back of the lecture theatre via the rear doors out into Piccadilly and then into the courtyard at Burlington House. Or if you're nearer the front, which not many of you are, then there's the door to my right, which I'll be using to go to the same place. At the end of Tim's presentation, we'll have a brief Q&A before we'll have some sponsored drinks by Mott MacDonald. So thank you very much, Mott. Yeah, then we'll have the brief Q&A will basically consist of me asking for questions, bringing a microphone to you. If you can state your name before you state your question, that would be great, because we've got some viewers online tonight, so it'd be good if they can hear what people are asking before we get an answer. So without further ado, I invite Tim up to present.
Thanks very much. Thank you and good evening. So today's talk is on the subject of geological influences on the Banja Hydropower Dam in Albania. Really, I should have slipped the word construction in there. It should be geological influences on the construction of the Banja Hydropower Dam, as you will see as we go through. So I'm now going to point that in the right direction and get the slide to change. So I'm going to start off by giving a bit of an overview of the devolved scheme very briefly and some of the brief details of the dam construction itself. Then I'm going to focus on the geology and geomorphology of the site, talk a bit about the construction, which started and then stopped and then started again, and then really focus then mainly on the job that I was most involved in, was the excavations and instrumentation of excavations around the abutments, which was the new construction. I was less involved in the actual construction, the raising of the dam, so I'm going to talk mainly about the excavations. One or two other matters if we get time. I'm expecting to speak for about an hour, but if we overrun then we'll see about that. And then return back to finish off how we finished off the construction of the abutment areas. So let's get this going. Okay, so just a quick overview then of the scheme. The location is in southern central Albania. As you can see there on the slide, it's the Devol River. So I'm going to have to put these on so I can read this small screen. And the Devol hydropower scheme consists of two sites, really. One is the Banja site, a 72 megawatt hydropower dam, which has been operating since 2016. And the second is the Maglica site, which is some kilometres upstream, which is a much larger dam. It's about a 165 metre high dam, and that's still under construction. So the Banja site is 80 metres high. It's got an operating head of about 80 metres. Discharge something like 100 cumecs, and as I say, the installed capacity of the power plant is 72 megawatts. The concessionaire is Devol Hydropower, or DHP, which is a subsidiary, special purpose vehicle of Statkraft, the Norwegian energy company, and they have a concession from the Albanian government to design, construct, and operate it for a number of years. The designer was AF Consult of Switzerland, the contractor, a JV between Limak of Albania and AGE of Turkey, and our role, Mott's, in a joint venture with Coin and Bellier of France, and now Tractebel, was to undertake the design review and construction supervision. So that's how we fitted in. So some brief details of the Banja Dam itself. Let's have a look at the overview of the site. So it's a clay core gravel embankment dam, some 960 metres long, 80 metres high. Total volume of the dam is something like 8 and a bit million cubic metres. And the reservoir formed by the dam is 16 kilometres long. Some other features, the spillway capacity is some 3,000 cumecs. And the head race tunnel starts at just over 6 metres diameter and reduces to 5. Just sort of cross-section through the dam so you know what the overall project was trying to construct, although I was less involved in this. It's a conventional gravel-shouldered clay core embankment dam. So you can see a clay core in the middle, filter layers either side of the clay core, and gravel shoulders. At one point, there was a thought to use part of the dam volume to dispose of some spoil that was coming out of the spillway excavation. But in the end, really because of programming issues, that was not taken up. That option was not taken up. So talk a little bit about the geology and geomorphology. Not all that much on the geomorphology. I think there's too many people in the audience that know a lot more about that than I do. But anyway, so just briefly on the geological context, the strata underlying the site, the solid strata underlying the site, were lower to middle Oligocene fleece deposits, part of the southern alpine fold belt. And superficial deposits included the river terrace deposits in orange here on a number of shelves or platforms along the sides of the valleys, and then river gravels, alluvial gravels along the floor, the base of the gravel. It's a fairly wide, flat river valley. And then draped on the higher slopes is a sort of thin mantle of colluvium. So looking at the superficial materials, this is just a view of a typical part of the river valley. Actually, it's right at the top end of the reservoir, and it shows you a terrace, a platform, which has been turned to agriculture. But actually, at the edge of the river, you can see river terrace deposits. So that platform is formed by river terrace deposits, but the river terrace deposits are standing, and they're gravels. They're standing vertically, whereas interestingly, the rock, supposedly the rock underneath, is standing at about 45 degrees. This is sort of counterintuitive, but it's because the terrace gravels have been cemented, and they're actually quite strong as a rock, and they will stand up vertically. The fleece bedrock is not very strong, and it's highly weathered, and is very susceptible to erosion of the river. On the bottom of that photograph, you can see the new alluvial material, which is sort of cobbly gravels being deposited by the river in the new floodplain. And this all shows quite clearly that periods of uplift. So at some time, the river would have been cutting a platform in the fleece at this level, and has deposited a thickness of gravels over a period of time, over quite a wide river valley. Those gravels have become cemented, and then for some reason, which we'll come on to, there's been a period of uplift which has encouraged the river to then cut down through that sequence, cut further down into the fleece, expose the old river terrace as a terrace, and then deposit alluvial materials across the floor of the new, slightly narrower valley. So what's the reason for that uplift? You might be surprised to hear that it's tectonically driven. I apologise for this slide. I had to sort of snaffle it off the internet very quickly at the last moment, just to guess. It's very much a cartoon sketch, but you can sort of see Albania tucked in there, just opposite the heel of Italy there. We've got a number of plate boundaries very close by, and in the area of Albania, we've got high compressive forces orientated in a sort of northeast-southwest orientation. The numbers apparently, though I haven't verified this, the numbers are the rate of movement of these plates in millimetres per year, apparently. So whilst the Arabian plate is taking it easy, going northwards at 15 mil a year, the Aegean plate is really motoring at 37 mil a year, going in a southerly direction. Anyway, focusing in a little bit more on the geology. Quite a complicated picture. That's a geological map of Albania. But you can see these compressive forces really creating quite a complicated system of thrust faults and superposition of older rocks on top of younger rocks. If you look at the, this one hasn't been, sorry, it hasn't been changed, but the colours are right. So you've got older ophiolite on top of slightly older fleche on top of younger fleche. And it's the younger fleche that affects our site. So, what are the implications of this for the rocks at our site? You won't be surprised to hear that the typical fleche lithologies, which consist of sandstones, siltstones, claystones, mudstones in repetitive sequence, thin beds generally, have been significantly distorted, as in the middle photo, by all this compression, all these compression forces. So whilst the overall dip is sort of in an east-northeast direction, that is from the left abutment or the left bank of the river towards the right bank of the river, there are significant variations all the way through and a lot of highly contorted beds in various places. So you end up with a rock mass with considerable structural complexity, as in the right photograph. And you may be able to see in that photograph that there are beds in various orientations, but I'll help you out a little bit. You can see that towards the left of that photo, you've got largely mudstone beds, which seem more contorted than the slightly more resistant sandstone and siltstone beds, which is what you might expect. But you can also see that the sandstone and siltstone beds on the right are not repeated on the left, and so there's obviously some kind of structural dislocation there as well. So it's really quite a complicated picture. And it's complicated, it complicates our ideas of strength as well as permeability. So these are all tectonically induced phenomena, but there's also the phenomenon of wild fleche. And let's try and get a definition of, or a genesis of wild fleche. This is a term given to some sort of soft sediment deformation structures. If you imagine you've got a basin near a plate margin that is continually subsiding, deepening, and you've got sediments forming within that basin, there will come a time when, as the slopes of the basin steepen, some of those sediments are then unable to support their own weight, and effectively you'll get gravity-induced slides on those slopes, and if a large sheet of the material slumps off down, it could well extend into the foreland area at on the bottom of the slope. So you get certain types of slumps on the slopes and certain types of slumps at the toe of the slope. And this has been a phenomenon which has been known for many years, although I must admit I learnt about it really since being involved with this project. And just to give you an example, again, snaffled off the internet, just some sketches of what somebody has seen. They've gone to the site and they've just sketched, this is what I saw. And you can see there's some really strange structures in here. And that's interesting because that is 1863. So these ideas have been around for quite some time. There's a paper about the geology of Canada. So just perhaps an example from our own site of this wild fleche. You can see you've got some fairly well-structured material there. And just to the right, you've got something going all over the place, broken beds, twisted beds, and so on and so forth. And this has implications, as I say, for the rock mass strength. So if we look at Hooke's method of deriving the geological strength index, their original methodology wasn't very suited to materials as heterogeneous as fleche. And so they did some work. 2001, they published a paper which was particularly aimed at this type of rock mass. and gave a bit of extra guidance for people trying to pick a number out off of a chart and make an assessment of what the GSI should be. But of course, on the left of this slide, we've got two different areas of our site, two different bits of fleece. So if you were in this area, you might say, well, this is siltstone sandstone, you might assess that, and you could have a GSI of 50, 60, something like that. But not far away, you might be in this area, and at the bottom slide, you can see there's an area of, again, to the bottom right of that, there's fairly well organised beds here. But in this area, it all goes to pot. This is wild fleece again. So if you're in that area, you might have a GSI value of, I don't know, 10 or 20, 15, something like that. So quite different rock mass strength. And what does that mean? Well, there's a lack of predictability. There's a definite lack of predictability across the site. And part of our job was to assess the rock excavations as they were exposed, and then to determine what rock support should be applied. So the rock support was typically sprayed concrete, mesh, rock bolts of various lengths, and the idea was that you would map the recently exposed rock face and select a particular type of rock support from a sort of a palette of standard details. You would say, well, I'll have a type A here, a type B there. Which is fine, but of course if the rock then varies immediately behind your rock face and you can't see it, then you can get things wrong. So, or even if you have an adaptable and flexible system, which you certainly need, you can't necessarily guarantee that you're going to get it right every single time, and this is a case in point. Just a word about groundwater conditions. The climate in Albania is obviously very hot in the summer and cold in the winter, but it's quite dry in the summer and winter, but the spring and autumn are quite wet. And you get heavy downpours, especially in the autumn. Rock mass permeability, as you might expect, is highly anisotropic and is complicated by these structural disturbances. So monitoring data is very difficult to interpret or extrapolate across any distance at all. So if you look at that slide, you'll see that the material to the top and the right of this sort of folded band is slightly darker, it's slightly wetter, it's actually damp, and whereas the material to the below and to the left of those beds looks as dry as a bone, which it is. I'll just point out there's a little drain pipe there. That drain pipe it used to produce a little bit of water. So if you imagine 2 piezometers drilled and installed to the same depth, but maybe 5 meters apart, the one on the right will undoubtedly pick up some response from the groundwater, and you'll get a reading. And even if the flow isn't great, you might well get quite a reasonable pressure in that piezometer. But you'll get absolutely nothing on the one on the left, and it's only 5 meters apart. So it's very difficult to sort of generalise and say what is the groundwater table, because it's so heterogeneous. Right, I'm going to move on now to talk about a little bit about the construction of the dam. The original construction started in the 1980s, and they achieved quite a lot. They managed to excavate the main central part of the dam across the main river valley and found the grouting gallery on the bedrock over quite a wide section of the centre of the valley. Where in the deepest part where the grouting gallery dips down, they managed to even get the clay core up and over the top of the grouting gallery as well. They constructed a bottom outlet with a gate tower so they could control the flow upstream, and they built the cofferdams upstream and downstream as well. On the left side of the job, they managed to get part of the head race tunnel constructed and through the headland to start the head race arrangement there as well. But they had a number of challenges, landslips, and particularly in the area of the surface penstock. They created a large landslip there, which they had to deal with. And also in the powerhouse excavation was quite tricky. construction in the end was halted in the early 1990s. I'm sure those challenges won't have helped, but it really was halted because of funding difficulties and also because of political upheaval. So just looking at, that's a part of the grouting gallery being constructed near the right abutment. There's the bottom outlet with its gate down. And that's the central area, which is, where they're laying clay core material. So when we got to the site in 2013, it looked a bit like this. On the left, you can see the cofferdams are complete. The grouting gallery is installed for, quite a long section of dam. And it's covered over in the distance. You can see it's covered over by the clay core. On the left abutment, the head race tunnel, as I say, was partly completed, but they'd created this, or they'd induced this landslip, and therefore they had to construct this sort of buttress tunnel thing to sort of safeguard the alignment of the future tunnel. They didn't install the head race tunnel in here, but they just created a space so that it could be installed in future. And that worked. I mean, the hillside was more or less stable after they built that large buttress. On the powerhouse excavation, that wasn't so good. They had a number of instability issues and it flooded, and so they hadn't made a lot of progress on the powerhouse excavation. So with the new construction starting in 2013, I'll just remind you of what the dam cross-section looked like, and then move on to slide. I think this is early 2014, showing you some of the features here. This is taken from the left abutment, looking over towards the right. So to the right, you've got the upstream cofferdam. You've got a clay core with the grouting gallery central to it, gravel shoulders either side, and in the distance, a spillway and the stilling basin. And this is where we're starting to pick up from where the previous contractors had left off. A bit more of a detail here. You can see as we got, this is a little bit later, the dam core has been raised a fair bit and the grouting gallery mostly covered now. You can see in the distance that they're starting to build the final part of the grouting gallery up onto the right abutment. The spillway is being constructed. On the dam itself, you can see they're constructing the clay core, the gravel shoulders, and the filter layers in between, being carefully constructed there. Just a few details of that. Placing the clay core here, dropping the material down, spreading it out, and then compacting it, generally sheep's foot roller. And you can see they're doing that in sort of close levels with the filter material, the shoulder material again, fairly only just above that. These guys are doing some testing on the filter material whilst they're still placing the gravel shoulder. Yeah, and there's more detail of compacting the gravel shoulder on the right there. So I'll just go back to that one. One thing you can pick up from this series of photographs is that it's not possible to raise one or other layer well in advance of another one. You've got to bring all the layers up more or less at the same level. Okay, with half a metre step here and half a metre step there, but basically you have to bring the shoulders up, put first up a little bit, then you put the filter material, then you compact the clay layer up against the filter material. And you can't race ahead with one or other layer. And that's significant for what we had to do a bit later on. I'll come back to that. So now I'm going to concentrate on the bit that I was sort of most involved in, I guess, the excavations for the abutments, and particularly the left abutment, which had some considerable difficulties. So the first excavation, though, we got involved with this powerhouse excavation, the one that had been troublesome previously. This is the first major excavation on the project, about 44 metres deep, and it's 15 metres below river level. And the idea was to excavate a batter, protect it, before moving on to the excavation of the next batter. And then as you got to water level, slowly reduce the water level a bit, excavate a batter, protect that, and move on, and so on and so forth. It wasn't thought a good idea to completely dewater the whole of the thing in one big go, because I thought it would precipitate a large failure. So it was a sort of stepwise process. You can see that one of the challenges we had is that the beds, the fleece beds, although variable in this area, were reasonably constant and dipped into the slopes on the south east, but out of the slopes on the southwest. And therefore, the slopes on the southwest were inherently less stable than on the other side. And you can see that from the photograph. It just looks, you can see over the years, these slopes have weathered down and come to rest at a much shallower angle than these slopes. The client was keen to try and minimise the amount of excavation that was undertaken in order to get down to foundation level for the powerhouse. And he was pushing the designer to steepen up the slope. And we, as a design reviewer, we were trying to mediate between them and say, is it possible we can put a little bit more support in and steepen up the slope to minimise the cost of excavation. And the designer relented and did come up with a slightly modified design with steeper slope angles. That unfortunately resulted in some failures in this area, and it meant that we had to do some further design modifications. I mean, in the end, we had to go back to the original slope angles that were originally proposed, and we also had to move this thing, which is the emergency outlet stilling basin. We had to move it about 10 metres in order to get away from some failures that had been induced. So this was, this slide shows, even in the reduced angle slopes, we ended up with some cracking and sort of incipient failures, but they didn't quite amount to too much. But this was a salutary lesson right at the start of the job that you had to actually respect the limitations of the fleece bedrock. It wouldn't do things that it didn't want to do. And so you had to be aware of what those limitations were, and that required very careful mapping, especially of the bedding orientations in all the exposed surfaces of the excavations. As here you can see, the excavation for that stilling basin structure has been pushed back, and even when we did that, you can see that we're still getting very close to a few little failures and some cracking across here and so on. So it was a good lesson to us all, and us as design reviewers as well, that you couldn't push it too far. Contrast that with the spillway and the stilling basin excavations, which are on the right-hand side of the project, on the right bank, and therefore in an area where the beds are typically dipping into the slopes. So you've got south-southwest facing slopes, bedding dipping east-northeast, thereabouts, very little groundwater, and therefore these slopes are inherently stable. They're quite steep and they're quite stable, and these guys here are putting in the temporary support. They're putting in the rock bolt support and the temporary support, which is normally just a bit of sprayed concrete just to hold the face together. They haven't even bothered to apply it in some areas because it's so stable in its own right that they just didn't need to. So they could just plough on, put the permanent support in, 2 layers of sprayed concrete, and the job was done. So these slopes in the spillway were completed without too many problems. Likewise in the stilling basin, this is the deepest excavation on the whole project, 54 metres. Slightly more complicated structures in the fleece in this area, but generally nothing too adverse. And therefore, again, with little groundwater, these slopes were completed without any major hiccups. Now this all was in contrast to what happened on the left abutment, which was our sort of bête noire. The left abutment excavation here, you can see in red is the grouting gallery. The excavation batters I've shown in orange, and they're all 10 metres high. So there are 3 batters there. That's sort of 30-metre high slope with 2 berms. And the blue is the head race tunnel, which passes underneath all these works. So this excavation is required, obviously, to be able to found the grouting gallery onto rock, and also to key the dam into the hillside. It's going to give the left abutment of the dam some stability. And it creates what we call the downstream shoulder area. So let's start. There was some difficulties up at the top of the highest part of the excavation, above the dam centre line, but these were relatively shallow and relatively minor. The more serious problems occurred on this, what we call the downstream shoulder area. So looking at those upper excavations first, the detail was to excavate the slope and cover it with a layer of crushed stone, which was supposed to hold the water back and allow it to pass over the rock and end up on one of the berm drainage system. We were a bit sceptical about this design detail, and it wasn't very long before our fears were realised, and we had minor failures like this occurring in the batters. They were all very shallow. When we exhumed some of them, we found that, yes, even though the fleece was very weathered, the structure of the fleece was intact, not very far behind the face, and where it was of the wrong orientation, then water was coming out on some of the beds and we'd get instability. And over a period of time, these instabilities spread, as on the right-hand picture there. But they were always fairly shallow, and they didn't cause, in the end, a major problem. We did, however, insist that the design detail was changed, so in the end, these top two batters were supposed to be stoned in this way, and we ended up insisting that this was a sprayed concrete batter. Although it's not particularly pretty, it did do a better job of supporting the slope. So then moving on to the downstream shoulder, this is just to show you the start of the excavation for the grouting gallery. We'll get down to the grey material is the fleece bedrock, the less weathered fleece bedrock, and this downstream shoulder has been created by the excavation and the natural topography on the other side there. So in March 2014, a small failure appeared at the toe of the downstream shoulder. Before an instruction could be really generated to decide what to do, the contractor had been in there, whipped in there and tidied it all up, excavated some material from the toe of the slope and battered it and said, oh, there we are, we tidied it up, it's all fine. Which of course wasn't actually the right thing to do because we were removing weight from the toe of the slip mass. So this ended up allowing the slope failure to sort of move further back up the slope. And over a period of months, by June, it was starting to threaten the area of construction of the grouting gallery, as you can see in the central. What was a small failure, a relatively small failure at the toe, now has progressed right up here and starting to threaten these batters. Even though we put in quite a lot of additional rock support, you can see the very close rock box in there to hold all this part together, there was very little we could do with a more weathered material because it wasn't really susceptible to being bolted into place. The contractor had a go at the movements were very much aligned with rainfall events, and then the contractor therefore had a go at trying to prevent water getting into cracks and sorting out its drainage and so on, but that was met with sort of limited success because it was very, very difficult to do. So because of the concern about the failure spreading, if you like, back up, back up this whole area and starting to affect the top of the dam site and maybe even going up further up the hillside. And just through those trees is an access road to a village, so there's a village public road up there. And because of that concern, and yet we weren't really able to get into that area. You can look here. It's very, very steep, very difficult area to get in to do any physical works, bearing in mind this is all moving already as well. It was decided that we would monitor over the summer period to see what happened and then determine what to do. So after much debate, a monitoring regime was agreed, and it included some inclinometers, some piezometers, and a number of surface movement markers. These were monitored 2 or 3 times a week, but more regularly when there was heavy rain. Some of the issues were that many of the instruments got destroyed quite quickly because of the high movements. The piezometers were not very useful at all anyway, because for the reasons I've already discussed. And some of the data that we had was incomplete, and the rainfall data was an example. Just to give you a little bit of the data from the inclinometers, inclinometer I1 was on the centre line of the dam. I apologise that these two graphs are not drawn to the same scale, so you have to read the numbers off the top. The inclinometer I1 on the centre line moved something like 18 mil at a depth of 3 metres. The depth of the moving mass was something like 16 metres. And there was a large increase in the movement in sort of February 2015 when there was a large rainfall event. But it's interesting to note that the pattern of those two graphs is actually remarkably similar, even though the scale is slightly different. Inclinometer I2 was in the area of the slipped mass on the downstream shoulder. It moved something like 45 millimetres before it became unserviceable. But the depth of movement was very much the same. It gave us the information that the slipping mass was something like 16 metres thick. But then that became unserviceable because it had moved too far. The piezometers weren't working particularly well, and so we were left with the movement markers. And the movement markers ended up being the most useful thing of all. So this is some of the data that we obtained from the movement markers, and this was sort of put together by our colleagues in Cornubellier, who were looking after the instrumentation angle. And you can see this is just an example, one of the examples of plotting displacements, but they also plotted accelerations, and it was possible to link the acceleration periods with periods of rainfall, unsurprisingly. So here's a sort of cartoon sketch summarising some of the movements that we got over a period of 8 months whilst we were monitoring. And some of these movements are huge. One of them, M6, moved 8 metres horizontally and 4 metres vertically, nearly 3.7 metres, over a period of 8 months. And that movement monument was still there and was still monitored over all of that period, which is quite an achievement, I think. It also told us, we determined that there seemed to be 2 areas. The bottom of the slope, whilst it was moving and some of the movements were reasonable size, it was of a different order to the upper mass, which was moving these large distances. So it seemed that the toe of the slope was acting in some way to buttress the upper part of the slope. And that was greatly to our advantage. It was doing a good job. And here on the bottom left, you can see that's just a record of M6, and you can see step-like changes, and all those will relate to rainfall events, although we don't have the rainfall data, unfortunately. So taking the story further on, by May 2015, you can see on the left-hand side the failure has progressed. But we've not got the catastrophic side. I mean, we were expecting the big one. Every time it rained like mad, we were expecting the big movement, which was going to mean that we had to drop everything and get in and charge about and do extra works. But it didn't quite happen. We kept monitoring. You can see there, that mass there was originally connected into this bit of shotcrete up here, and it sort of moved, well, that's 5 or 6 metres, or maybe 8, that's 8 metres. But it was just sort of progressive and gradual, and we were able to just keep an eye on it, fortunately. Later on, there were other rainfall events, and we ended up with some further cracking of shotcrete and cracking of the berm, and this became a bit of a concern, and again, extra support was put in around this excavation while they were finishing off the grouting gallery and the grouting gallery access tower. But overall, the upper slopes remained reasonably stable, and construction was not interrupted. So I'll just finish, that's on the downstream shoulder. Just one quick slide on the area around the intake. So there was another excavation upstream around the intake to the headrace tunnel. This created an upstream shoulder, and that upstream shoulder was also subject to some failure. So a slip occurred, it was noticed, and in the same way it too was monitored, It didn't have quite the same profile, that some of these are related to rainfall events, but it didn't seem to be quite so clear. But it was more of a progressive failure over a number of months. The toe of the failure came out, fortunately, just above some works. This is what they call the Sedicon pipe, and you can see all the shotcrete is cracking up here, and this is the toe of the slip emerging on the dam side, or the dam excavation side of that ridge. So what was done here was there was the opportunity to take a bit of soil off the top and release the load from the top of the slip, and that generally was enough to slow it down and make sure that we didn't get a catastrophic slide there as well. So just finish on those works, and we'll come back to that in a bit, but I'll just touch on some other matters if we're not doing too bad for time. Yeah, we're fine. So just a bit about the Grout Curtain. So, as we've said, they'd already constructed in the 1980s a considerable portion of the grouting gallery, and they'd done the Grout Curtain over a reasonable section as well. So this previous work was verified by check holes, and I believe some additional work was done to upgrade it. The new curtain was a 3-line curtain, as you can see in the sketch there, with conventional cement-based grouts used to form the cut-off, and the gin method was used to inject the grout. So just putting a little bit of colour on there so you can see. So that's you can see the dam at the top in the reddish colour. The extent of the grout curtain is in the beigey colour. Interestingly, the planned extent of the grout curtain from the 1980s work was about half the height or half the depth of what was finally installed in the more recent construction. So we were being more cautious with the extensions of the grout curtain. As I say, the gin method was used. It's just an extract out of one of the reports on the grout trial, in which the data was analysed in order to set the gin numbers for different depths so that injection could take place without causing hydrofac. And again, going back to the fleece and the geological controls, you can see that if you were trying to inject grout into this sort of rock, you get a very different grout take to if you were trying to inject grout into this type of rock, and so it transpired. And the sort of grout takes varied from 0 to over 200 kilograms of cement per metre of grout hole. And just to sort of summarise that, again, our friends in Cornebellia did some summary graphs and whatever of this, the grouting work. And you can see how variable it is, and this is all to do with the nature of the fleece. One other little anecdote was that in the powerhouse excavation, we ended up with some hot springs. Some hot water appeared right at the bottom of it, and it was rather sulphurous and foul-smelling. And there was some concern about mineralisation and aggressivity to concrete and so on, and it was found to be high in sulphates. So checks were undertaken to make sure the concrete would be adequately protected. It was interesting that. Should we have any ideas, or should we have been surprised at finding that? Well, when you find out that the word Banja means baths, perhaps we shouldn't have been surprised. But I didn't know that until we found this water. So there we are. Right, so now on to the completion of the construction. So the left abutment, this difficult area on the downstream shoulder, what's the permanent remedial solution? Well, it wasn't very long before we started to think that some kind of large stabilising berm would be the best idea, because we've got a cheap available material, we've got an established specification for the material, for placing the material. It would be a robust and permanent solution requiring no maintenance in the long term. The reason it was cheap is just so happened that in the contract, the contractor had put in a low rate for that material, and therefore it was an opportunity in a way for the client to do some works without excessive cost. The problem, however, was the programme, and the programme was entirely driven by the dam construction. Now, you remember we said that you can't raise, say, the shoulders miles and miles above the filter miles and miles above the clay core, you've got to do them all sort of in sequence. And so what we'd like to do here is put 30 metres of material on the bottom of this downstream shoulder overnight and stabilise it, and that will be the end of the problem. But we couldn't do that because we've got to raise the whole dam up to get to that level. And it's a long dam and it's a big area and it's a lot of clay. And so this process was very much held up by the need for quality control in the placement of these materials. We couldn't compromise on the quality control in this area just so that we could haul some material in here. In this picture, you can see what they're trying to do here is actually put filter material on the contact between the shoulder material and the rock that they're trying to stabilise, so that it would be properly filtered and we wouldn't have any movement of particles in that area as well. But just to describe how the idea of the stabilising toe berm developed, that's a plan of the dam. I'll just put the outline of the dam on there, and just for reference, the crest level is 180 metres. So the first idea was to have a toe berm in with a crest level of 148. But we, through quick discussions with the designer, we quickly determined that wasn't going to be adequate, and they revised the plan to go up to 160 metres. But as you can see, that's still not really totally protecting that downstream shoulder, and we could still have instability issues which are going to creep up the slope. And this feature here is the road that serves the village higher up the mountain. So we were worried about that, and through further design review and interfacing with the designer, we said that you should increase the height of the toe berm and wrap it around the nose of the downstream shoulder and protect it in that way, and that would stabilise that and the road. And in fact, it went further than that because there were still further failures or movements that could have led to failures, and in the end we suggested that they should actually raise it even further. So this was actually sketches that I did as part of the design review process. We were backwards and forwards discussing and commenting on stability analyses that were being done and so on in order to get to the right solution. So in summary, the toe berm height was raised as part of the design review process, and the various failures that were occurring during the works only served to support the idea of increasing the height of the toe berm and making sure it was robust enough. The total volume in the end was 68,000 cubic metres, and once it was constructed, of course, the movements subsided. So now just some photographs of what we ended up building. This is a view along the back of the dam, so the downstream face of the dam, and in the distance, that's the toe berm up there. A bit of a closer view, and you can see the toe berm. It's very difficult to see without me highlighting them, but they're different levels with benches in between. And in this one, you can also clearly see the road that goes up the hill to the village. Indeed, they raised the toe berm in the end really quite over a large area to dam crest level, and even did some further work with bolt fill just to support the road there. Here's a sort of panorama view looking down from the top, from the road onto the top of the toe berm. And here's a view from the left abutment where we had a view several years earlier, looking along the crest of the dam as completed. This area here is part of a similar buttressing effort which went into supporting the upstream shoulder, which is this bit of land here. And that's the intake tower with the gate towers and bridge access bridge to the tower. Oh, that's the Sedicon pipe sticking out of the water there as well. So here's an aerial view of the site. You can see the stabilising toe berm on the downstream side. You can also just see the intake works where there's very similar sort of stabilising work having been completed there. So it only remains for me to say some thanks. Thanks to our client, Devol Hydropower. Bord Aspen was our main contact. Our partners in the Macdonald Cornubellia JV, Philippe Crosnier and his many colleagues, and Mark Gill of Mott MacDonald, and many others. I can't mention them all. But especially I want to say thanks to the geological team, Mara Pudu, Pierre-René Carré, and Meggie and Scott, who are in the photograph there, who did a lot of running around in the rain, trying to log things and give us information so that we could select the right slope support and take the necessary steps to keep the job stable. But at that point, I'll stop and say thank you very much for listening. I'll invite some questions. Maybe I'll put this slide up so that you can see that one as well.
Right, guys, so have you got any questions on the floor? If you want to raise your hand.
David Nobbery. Interesting thought that you had quite significant movements on that left abutment. I mean, metres is large by any reckoning, particularly on a water retaining structure. Did you have any concerns about loss of integrity of the remaining ground as a result of all those downslope movements, given that there's a path for water to come round the edge? Is there not?
There is, and yes, we did have concerns. So the first concern was, would there be voids in this slip mass, and so on and so forth. And so there was a lot of work done on the filtering arrangements. So the tow berm, which was going to basically act as a great lump of weight to hold the thing in place, had to be adequately filtered. So all the filtering arrangements that were necessary for the clay core were repeated when we were putting the tow berm up against. So that's that part. And then the next thing was to make sure that the grout curtain was adequately QA/QC'd, if you like, was extended to the right amount, so that actually the flow path for anything getting round that end of the dam was so long that it wouldn't have a destabilising effect. But absolutely, it was a concern with all that movement and the lack of integrity of that material, for sure.
Any other questions? Another one from...
Sorry, David, carrying on. So are you, because you're putting all these filters in, which is brilliant, it stops the particles moving within the soil, but it does actually give you a path, water path.
Well, if
or is it the geometry?
Yeah. I'd have to show you the geometry of it. Essentially,
it might be a bit complex, so I'll let you off that.
Yeah, I can't produce a 3D model just right here, but yeah, essentially. I suppose there was less material on the downstream shoulder than there would have been if some of that hadn't slipped off. But nevertheless, the design was reviewed such that it wouldn't be a problem, basically, either from stability point of view or from a seepage point of view, for sure.
Stephen Jeffries, probably not in your patch, but would you be able to say anything about the grout mix design at all, what grouts we used, other than it was cement?
I know it was just a traditional cement-based grout. I don't know the details because we weren't supervising that. I know they did the gin method to inject it, and I just presented some of the results. So it wasn't my area, I'm afraid.
Thank you.
Sorry, Ed Russell, Mott MacDonald. It's just for a bit of information, really. It's in terms of you talked about the variability in the GSI for the fleece. In terms of like the typical designs that you came up with, if you were going between materials with a 60 and a 10, like what was the kind of range and difference between your bolt lengths for your typical details? Just a feel for it.
Ballpark, because don't forget, it's not our design. It was AFC's design, and we were just implementing it on site. So I think it was more. I think they were either 4, 6, or 8 meters long bolts, and spacings. Yeah, the spacing would have varied a little bit, but from probably 1.5. In the most intense area there, we've got bolts at really quite close spacings, up to sort of random bolts at maybe 3 or 4 meters or 3 meters, that sort of distance apart. What they did with the thickness of the shotcrete, I can't remember the thickness of the shotcrete, but so there's a reasonable range, but. In some places, you got to the point where the material was almost like a soil, and then you had to decide what you were going to do. You're either going to just remove it. It's not rocky enough even to rock bolt sort of thing. So at that point, you'd have to come up with a different solution, which we did in some places.
Thank you.
Any other questions from anyone on the floor?
Jim Gelder. There's a lot of extra costs there. Who carried the risk of all of this? Was it the client, the contractor, the designer, the design reviewer?
Jim promised to ask a question that I couldn't answer at some time, and he's delivered on that promise. I cannot remember. I believe
Not the design reviewer then?
not the design reviewer, as it happens. No, not the design reviewer. We had a great sympathy with the contractor, but also with the designer. One of the difficulties was we wanted to instruct, or we suggested that they did some works much further up the slope, try and get drainage works in, try and get the water out the slope, manage the water better. I haven't talked very much about drainage. There was a battle really to get the contractor to manage the water well, but there were things that we could have done further up the slope which would have helped. And of course, that was a problem because you couldn't instruct the contractor to do some works outside of the construction site. There was a contractual issue there, and we didn't have access to the land, so that was a problem. So I think those things where where the contractor had caused a problem, I think he picked up the tab. Now, how the split was on the stabilising berm, because really that was a very, very susceptible part of the construction site anyway. Now, whether the cost of that was shared, I don't know. I wasn't involved in those sort of discussions. Certain areas, they would certainly have had cause to had a justification for a claim because it was very, very difficult to work in certain areas. I can't answer the question in detail, I'm afraid. That's fair enough.
Okay, one last question.
Do you know what the project lifetime was that's estimated with it?
Design life will, I imagine the design life is nominally 60, but the dam will be 220, I'm sure.
220.
Yeah, it's 120 years life, I would have thought, unless there was something different or odd about this one, but it normally is 120 years.
Okay. Thanks very much, Tim.
No problem.
I'm sure everyone will agree that was a great presentation. Before we go through for some sponsored drinks by Mark McDonald, I'm just going to cover a few points for the engineering group. Thanks, Tim. So the next meeting we've got is the Glossop Lecture, which Kevin Privet is receiving this year, and that will be at the Royal Institution on the 14th of November. So please all come along. There's no registration required for that event, although the reception meal afterwards, which we'll be hosting here, you will have to register for. We're just in the process of setting up that registration page at the moment, so you'll see some emails flying about and the website updated in relation to that soon enough. And then a bit of a different event this year. In December, we'll be having a Christmas social, so it's going to basically take place at Imperial College, London, on the 5th of December, and we're going to have a quiz night, really. So a bit of a networking event, something for you to all kind of relax and enjoy and integrate with everyone at. So there'll also be a registration process associated with that and a fee for each team. So, but you'll get more details about that in the coming weeks. All right, so now we'll just go through and have some wine and beer and soft drinks as well, if you prefer, on behalf of MOTS. So thanks all for coming, and we'll go to the lower library now.